Hello, class. Welcome to the next segment in Lecture 21. And in this segment, I do want to talk about a few of the glaring assumptions that we made in our math of the previous segment before proceeding on to some of the parameterizations. This is kind of an intermediate segment, but it also contains some very important information. So let's just go ahead and quickly cover some of the concepts that are relevant to what we just did. So when we derived our equation for the buoyant force, that is the net acceleration of an air parcel based on the temperature of the air parcel and the temperature of the surrounding air, we only considered buoyant force and the force of gravity. But of course, there are other forces that are acting on the air parcel that also should be considered. So in that case, we only considered by using virtual temperature, we considered the contribution of water vapor to the density of the air parcel. And that means that since we're considering only water vapor, we're not considering liquid water. And of course, as an air parcel rises upward, it's going to be expanding and cooling. And in that process, it's probably going to be condensing water out. And if you're condensing out liquid water, the force of weight of liquid water is much greater than the force of weight of just water vapor. So that's something that we ignored. And the technical term for that is hydrometeor loading, which of course, again, as the air parcel wants to go upward, you might have liquid water in there. That's going to increase the force of weight, and that's not something that we accounted for in the equation that we derived in the previous segment. So just something to keep in mind. There are some physical processes that we are ignoring. And there's actually 4 different processes that we've ignored, the first of which we're looking at on the screen right now. The second process that we ignored is the technical term for this is perturbation pressure gradients, but basically what happens is if you've got a rising current of air, you're going to be compressing the top of the air and leaving a wake behind the rising air. So as this air parcel rises upward, it's going to be compressing the air above it, which is going to result in a region of high pressure, a local, very small region of high pressure. And then as the air parcel accelerates upward, it's going to leave a wake of low pressure. So this is kind of the same mechanism where if you're driving, say, really fast, you're going to be displacing air. You're going to wind up with a region of relatively high pressure air in front of your vehicle and an area of lower pressure air behind your vehicle because you're displacing air as you're moving forward. And it's kind of the same mechanism here. As the air parcel rises, it's compressing air ahead of it and leaving a wake of lower pressure behind it. And that would then dictate that we have a pressure gradient force acting against the air parcel's motion, because as the air parcel is going up, you've got higher pressure up here, lower pressure down here. That means that there's a pressure gradient force that's trying to force the air parcel back down. And again, that's a mechanism that we didn't account for when we derived our equation in segment 1, because this process just gets really complicated, and it's something that we kind of want to ignore if we can, but sometimes that's just not the case. And just keep in mind that these processes are in fact involved in the real atmosphere. Another force that we did not account for in that equation was the force of friction. And of course, if you've got an air parcel that's moving upward, then there's going to be some sort of frictional force that's trying to oppose it. So that's just sort of an extension of what we talked about in lecture 6 and 7. This is just now looking in the vertical direction as opposed to the horizontal. And another thing that is not accounted for in the equation from segment 1 is as the air parcel. Of course, when we made this, when we took a look at the air parcel in segment 1, we made an extremely glaring assumption where we're going to assume that the air parcel itself is referred to as a closed system, which means it's not exchanging matter or energy with its surroundings. Of course, there are not these pockets of air floating around in the atmosphere that are completely isolated from each other. That's just not how the atmosphere works. So, of course, there's going to be some sort of turbulent mixing as the air parcels are ascending upward. And that's something that we're not accounting for. And this can actually have a significant impact on the properties of the air parcel itself, because as you've got relatively warm and moist air rising, we'll just use that as an example, it might be rising really rapidly, which is going to result in a lot of turbulent mixing, and usually the surrounding air is very cold and dry. So if you're mixing cold and dry air with warm and moist air, you're making the air parcel more dense, so you're going to be reducing the amount of buoyancy that it has. And this is especially important if the updraft is particularly strong. If you've got a really strong updraft, you've got much more turbulence acting on the air parcel, which means you're going to have a tendency for more mixing between the air parcel's air and the surrounding air. And we'll kind of talk more about this idea of turbulent mixing when we talk about the atmospheric boundary layer, which will follow the severe weather unit. But I just wanted to cover some of the physical processes that we ignored in the first in our derivation of the equation in segment 1. These processes are important in the atmosphere, but the math behind them is so ugly that we like to just ignore them. But that's going to do it for this segment, and in the next segment we will actually start getting into some of the parameterizations of buoyancy. So with that, I will see you all in the next segment.